Galaktički kosmički zraci, satkani od visoko energizovanih teških jona, prožimaju cijelu našu galaksiju, ali srećom ne dopiru do naše planete. Srećom, zato što bi ova jonizujuća zračenja razorila život na Zemlji. Zemljino magnetno polje svojevrsni je štit kroz koji teški joni ne mogu da prođu. No oni se ipak pojavljuju u našem okruženju. Na planetu Zemlju dovodi ih nauka. U laboratorijskim uslovima u 14 naučnih ustanova i klinika u svijetu proizvode se teški joni koji se u akceleratorima ubrzavaju dostižući velike energije jer imaju veću masu nego druge čestice. Teški joni su atomi koji su izgubili neke ili sve svoje elektrone i time postali čestice pozitivnog neelektrisanja. Zovu se teški jer dolaze od elemenata visokog atomskog broja i atomske mase. Tako su, na primjer, gvožđe, uranijum, ugljenik, elementi koji mogu da formiraju teške jone. GSI Centar za istraživanje teških jona u Darmstadtu u Njemačkoj jedna je od rijetkih ustanova na našoj planeti gdje ove čestice nastaju u eksperimentalnoj sredini za potrebe naučnih ispitivanja. GSI ima 1600 zaposlenih, a uz njih je angažovano oko 3000 gostujućih istraživača, studenata master i doktorskih studija, postdoktoranata iz 200 ustanova iz 56 zemalja. Naučnici iz svih krajeva svijeta ovdje koriste teške jone za istraživanja u nuklearnoj fizici, nauci o materijalima, proučavanju zaštite astronauta od kosmičke radijacije, ali i u liječenju kancera. Upravo ovdje u GSI-u izveden je prvi eksperiment sa teškim jonima na svijetu. Nakon toga uslijedio je još jedan važan korak. U ovoj radijacionoj hali 1997. prvi evropski pacijenti liječeni su hadronskom terapijom kancera. Pokazalo se da su teški joni bili spasonosni za 440 pacijenata oboljelih od kancera glave i vrata, kojima je ova, u to vrijeme potpuno nova terapija, bila posljednja nada. Ono što je krajem 90-ih bio eksperimentalni tretman, danas je priznata terapija čija je cijena prilično visoka jer su akceleratori sa teškim jonima veoma skupa tehnologija. Zato se njome liječe 4 kategorije oboljelih: djeca, trudnice, pacijenti čiji se tumor ne može operisati i pacijenti čiji je tumor otporan na konvencionalno zračenje. Tako se ostvarila vizija naučnika koji su još sredinom 40. godina prošlog vijeka na čuvenom Berkeliju naslutili da se ubrzanim česticama može liječiti kancer.
This is an interesting history because it goes back to the time of the Manhattan Project even. There is the famous movie Oppenheimer now that everybody has seen. And actually Lorentz was one of the collaborators of Oppenheimer and he invented the cyclotron, so the first accelerator. And then one student of Lorentz, whose name was Robert Wilson, he looked at the potential of this new accelerator and he saw one thing which is called the Bragg peak. So he understood that if you use particles, most of the energy is deposited at the end of the range when the particles stop. And he published a famous paper in 1946, so many years ago, that was indeed called On the Applications of Protons in Radiotherapy. So he understood that you can use particles to destroy tumors. Since then there were many studies, many developments. And then in the 70s, in Berkeley, again, the Lawrence Berkeley Lab, so the lab founded by Lawrence that got the prize, of course, is Nobel Prize for the invention of the cyclotron, they started to treat patients with different ions. They use protons, they use helium, carbon, nitrogen, up to very heavy ions like neon and argon.
Prva probna zračenja na Berkeliju potvrdila su vizije Roberta Wilsona i mada nisu bila najbolje isplanirana, pa samim tim ni potpuno uspješna, otvorila su vrata za ovaj terapeutski pristup koji privlači pažnju naučnika širom svijeta.
The first to catch up this idea were the Japanese. So the Japanese already in the early 90s started to treat patients with carbon ions in Chiba. And then comes this institute, GSI, under the direction of Gerhard Kraft. He had the idea, he was in Berkeley, of course, so he studied in Berkeley, understood from Berkeley how it worked, and he decided to import it here in Europe. So the first patients was treated at GSI in 1997 with carbon ions, and since then this therapy has largely expanded in all over the world. At the moment, there are about 110 proton therapy centers, so centers where patients are treated with protons, and about 14 centers that also use heavier ions, like carbon ions, for treatment of resistant tumors.
Od 90. godina terapija se znatno proširila po cijelom svijetu. Osnovane su bolnice za takozvanu hadronsku terapiju kancera, a u istraživačkim centrima kao što je GSI decenijama se predano radi na unapređivanju različitih aspekata ove metode kojom se skoro potpuno čuva zdravo tkivo oko tumora.
From the physics point of view, protons and carbon ions are similar. They have the same advantages in comparison to X-rays. With X-rays, the dose on the skin will be always higher than the dose to the tumor. So if you irradiate with only one beam, you will kill the patient before killing the tumor, because the dose to the normal tissue will be higher than the dose to the tumor. So what you have to do with X-rays, you have to rotate the beam around the patient so that you crossfire your beams on the tumor and you have a higher dose to the tumor. But of course, if you rotate the beam around the patient, you will irradiate a lot of normal tissue, so you will have a lot of toxicity. All the dose to the normal tissue is not good dose, it's bad dose, because it's only side effects and no advantages in curing the tumor. If you use particles, both protons and carbon ions, you can exploit the Bragg peak, so this high deposition of energy at the end of the range, and then you can only use one beam, two beams, and so you will have a very little exposure of the normal tissue and very high cure of the tumor.
We are in the center where the carbon therapy was first developed with the scanned ion beams. And they're usually advertised like the beams where you have the Bragg peak. Dose distribution means that you can use it like a sharp bullet to tackle the tumor precisely and giving no dose to the normal tissues around it. But in reality, you have to be very careful with this approach, because if you miss the tumor slightly, you might end up in a healthy tissue or in some clinical organ. Means you have to plan the treatment very wisely. So normally when you do it, you do the scan of the patient, the CT, and then the oncologist is drawing the contours of the tumor, of the organs that need to be spared. Then the medical physicist is preparing the treatment plan, and then this treatment plan is delivered to the patient. But there can be some daily variations in the anatomy, for example, like the patient was totally healthy on the day of the scan, and we are speaking, for example, about the head and neck tumor, and on the day of the irradiation, the patient is slightly cold, so the nose gets a little bit blocked, and it would mean that if we deliver the plan to this patient, the calculation of the anatomy and of the beam path is not really correct anymore. And this is of course dangerous, because in this case we might end up not in the tumor, but for example in the optic nerve. And we will neither treat the tumor, but on top of that we will cause extra damage.
Kako bi se ovo izbjeglo, pažljivo se sprema plan zračenja za svakog pacijenta. Pošto je pokretanje snopa teških jona u akceleratoru dosta skupo, istraživanja se često rade na simulacijama pomoću svojevrsnog digitalnog dvojnika snopa jona.
We plan how can we best have the treatment go where it should go, and the facility here is actually a prime opportunity to test this out in real life. Because we have a setup where we can test the ideas that we developed in simulation experimentally, by delivering the beam to moving objects, like for example, small tumors that are moving on some movable stage, or breathing phantoms, something like this, breathing like plastic versions of the patient. So of course this is not a ready-made protocol. You cannot go into the treatment unprepared. So what you do prior to the treatment is you image the patient. Typically you do CT, MRI, PET, and you use this information to firstly define where is the target that I want to treat. Where is my tumor? Where do I want to steer the radiation to? When you know where your target is, you conduct what we call a treatment planning study, which means you optimize the irradiation using like a mathematical theory and a simulation of the beam. You optimize the irradiation given to the patient to reach the radiation dose to the tumor that you want, while minimizing the dose to the healthy tissue. You want to spare that as much as possible. And then when you're done with this is what we call a treatment plan. And you can import that to your system, and the system will then irradiate that to the patient. And when I say studies, because we as a research environment, we don't have patients coming in to irradiate patients, but we just try to understand how can we improve that process to better shape our treatment to the patient to get the best result for them.
Ova istraživanja su veoma važna jer se disanjem tumor stalno pomjera. Ako se nalazi u grudnom košu, abdomenu ili oko karlice, tumor se neznatno pokreće disanjem, pa se tom pokretu mora prilagoditi tretman pacijenta. Pošto ritam disanja također može da se mijenja, što onda remeti i najbolje planove zračenja, idealno bi bilo kada bi snop bio vidljiv i upravo u tom pravcu se kreću razna istraživanja. Čitavi timovi stručnjaka rade na više paralelnih projekata. U jednome od njih koriste se radioaktivni snopovi teških jona.
The beam that we use to treat the tumor is not a stable beam of carbon-12, but it's a radioactive beam of carbon-11. Why we like it? Because carbon-11 allows you to use PET, positron emission tomography, to see the beam. So while we irradiate with carbon-11, we can see where is the beam using a PET camera, positron emission tomography camera. So we destroy the tumor, but we see the beam. So if the tumor is moving, we can actually move the beam to follow the tumor and to destroy it. Especially will be very useful when you treat tumors in the thorax, like lung cancer, or in the abdomen, like liver cancer, colon cancer, all organs, even prostate cancer, all organs that move during the treatment. For the abdomen, also breast cancer, of course, that's also moving.
Carbon-11, from a radiobiological point of view, perform in a very similar way to the carbon-11, to the carbon-12, but when the beam stops, it decays and produces photons that are detectable. So in this way, it will be possible to automatically treat and in a simultaneous way getting an image of where the beam was stopping and if my treatment and my Bragg peak is positioned properly inside the patient. The production of this ion beam is challenging. This is one of the main reasons why it was not done before. So the idea is known since a long time, but it's very difficult to produce this kind of beam with intensities that are reasonable for clinic and with the purity and beam characteristics that are qualitatively sufficient for clinic.
The problem with the carbon-12 is that only the small fraction of these particles, of these fragments, are radioactive in the way that we need them to be. So we get a very low signal. And it's not the signal that is coming from the particle that we are shooting at the patient. These are some other particles. So we cannot really say with the sub-millimeter precision where is our beam. So there is always still some uncertainty. So there is now an idea to try to shoot directly the fragments of this beam. So they should have, in theory, the same biological properties, but the PET signal will be much more high and correspond to the position of the beam.
Unapređenju terapije teškim jonima sve više doprinosi i primjena vještačke inteligencije. Algoritmi se koriste za analizu velikih baza podataka koji se odnose na pacijente kao i na simuliranje različitih scenarija u procesu liječenja.
AI is a really wonderful opportunity which can learn things we cannot do as people, as human beings, but the results should be double checked because it's a black box and we cannot follow step by step how it gets the results. It should be also checked all the opportunities whether the data can be perturbated, whether it's a good data because it's as good as our data are. But it's still a very good tool to help people, to help doctors to save the time, to see something maybe what they don't see, they did not pay attention to because it's some little details which are like each 100 patient or each 1 million patient has. And in any point we still should check it. We should not trust it blindly, but we should trust it enough to use it.
Već postoje softveri koji na snimcima automatski razgraničavaju tumor od okolnog zdravog tkiva, čime se štedi veliko vrijeme i energija, a veoma je korisna i primjena vještačke inteligencije na utvrđivanje obrasca disanja kod pacijenata oboljelih od tumora pluća.
Lung tumor is one of the most difficult tumor to treat because lungs move a lot, and of course tumor moves together. And if we use carbons, it's very easy to overshoot and damage part of lung or heart, depending on the angle you use. And AI can help to predict where your tumor is going to be, that our treatment can be delivered exactly to the point where it's going to be now. And of course, for treatment planning as well, if you have some pattern of breather of the patient, and you can predict what happens before, like shortly before the patient going to cough, because this patient, they have a lot of difficulties also with breathing, and they can cough or they can have a flat breath or different pattern in comparison to CT, which they had. And if we can predict what's going to happen, it can help to do it precise and to get less side effects of the treatment.
U grupi za biofiziku vrijedno se radi i na raznim drugim temama. Tako su naučnici otkrili da bi uvođenje pacijenta u hibernaciju dovelo do prestanka rasta tumora.
It's very old studies also showing in the hamster when they induce osteosarcoma on this hamster, and when this hamster goes to hibernations, the tumor is stopped growing. It's very interesting because they compare between the full awake animal and the hibernator. The size is different, but unfortunately in this case, when the hamster is aroused, the tumor is growing back. So that's something that we don't want. So here in GSI, in the clinical radiobiology group, because here we have a radiation facility, we try to think that if we combine between hibernation and radiation to cure also cancer patients.
Hibernacija se istražuje na pacovima jer oni, kao ni ljudi, ne ulaze prirodno u ovo stanje.
In nature, for example, squirrel, they go hibernate, and then hamster, they also go hibernate. They same rodents, like I mentioned before. Mouse, they're going for naturally go to torpor or hibernation. When we put the mouse in the low temperature, room temperature, and no food, they go hibernate naturally. Rats is more like, because as I mentioned, rats is non-hibernator, and we are human are non-hibernator. So if it's applicable to rats, so hopefully in future human also, this also can be applicable for human. It's always have to test it to the animal that's similar to us. So that's the reason why we're using rats.
Za sada se pomoću određenih lijekova pacovi mogu uvesti u stanje koje samo podsjeća na hibernaciju.
I cannot strongly say that what we are inducing now is like a natural hibernator, because natural hibernator have, for sure they are going to hibernation or torpor because of the environment changes, like the cold, extreme no food conditions, less food, and then the metabolism is going down first, gradually, slowly, and then the body temperature followed. What we are trying to do here is by chemical induce is very fast. It's very quick. It's so different, so much different. That's why a lot of studies still needed, because it's not well understand if actually the body temperature is down and then the metabolism down, or the metabolism first down and then the body temperature is down. But for sure, it's not gradually, it's very fast. So our studies, we also measuring basically like after we inject, and then we give it, we test it like 5 minutes later, half an hour later, it's already down basically. It's very too fast. So that's why we just saying it like hibernation-like, not really hibernations.
Za razliku od istraživanja poput ovog, koja se mogu obavljati na životinjskim modelima, ima mnogo tema koje se ne mogu dokučiti eksperimentima na životinjama. Tako je recimo istraživanje uticaja zračenja na pacijente koji imaju tumor mozga. Zato se u centru GSI uzgajaju organoidi mozga, minijaturne i pojednostavljene 3D verzije mozga proizvedene u laboratorijskim uslovima.
So in the beginning we have some pluripotent stem cells. So the cells have the capacity to grow in all different tissues from the body. So they can build heart or brain or liver or something like this. But in our lab, for example, we are very interested in brain. So in the beginning we have some media or like this feeding liquid. There are, for example, like nutrients and sugar inside. So everything what the cells needed to be, to grow or to live. And afterwards, when we want to push them into the neuron direction, we give them some different media and also adding some growing factors so we can push them to differentiate into neuron direction. And when we have these organoids with the neurons inside, we can keep them for a very long time. Until this point we want to have them, they are representing the adult brain. And afterwards we can use them for irradiation and to test how the irradiation affects an adult brain.
Protokol za generiranje cerebralnih ljudskih organoida je prilično dugotrajan proces i potrebno je otprilike 60 do 100 dana kako bi od matičnih stanica uz dodatke raznih faktora rasta i u posebnim uvjetima u laboratoriju nastala takva jedna struktura koja sadrži stanice kakve su prisutne i u ljudskom mozgu. Taj proces, iako je dugotrajan, skup i zahtjeva dobru kontrolu kvalitete modela, se isplati jer se organoidi mogu održati do 2 godine u kulturi, a ponekad i duže. Organoidi mozga mogu oponašati cijeli organ ili određene podregije u mozgu, na primjer moždanu koru ili hipokampus. Te regije su jako bitne u kontroli emocija i ponašanju. Tako da organoidi koji predstavljaju te regije se mogu spojiti u takozvani asembloid. Asembloidi su jako bitni u istraživanjima konektiviteta ili povezanosti između pojedinih moždanih regija, a koje mogu biti narušene u bolestima poput depresije, šizofrenije, ali i kao posljedica zračenja. Istraživanje utjecaja zračenja na ljudski mozak jako je bitno. Na primjer, slučajno izlaganje visokim dozama zračenja prilikom nuklearnih katastrofa, izlaganje astronauta kozmičkom zračenju u svemiru prilikom dugih misija kakve su planirane za budućnost, ali izlaganje zračenju u dijagnostičke i terapijske svrhe može biti štetno jer može imati štetne posljedice na promjene u ponašanju i kognitivne deficite. Mehanizmi takvih promjena nisu dovoljno razjašnjeni i budući da ih je nemoguće istraživati na ljudskom mozgu, a jednostavne stanične kulture i životinjski modeli ne nude dovoljno uvida u mehanizme nastanka tih štetnih utjecaja u čovjeku, potrebni su novi modeli koji to omogućuju poput cerebralnih organoida i koji mogu oponašati određene aspekte ljudskog mozga.
Razotkrivanje ovih mehanizama moglo bi da pomogne naučnicima da bolje razumiju funkcionisanje mozga, efekte koje zračenje ima na mozak, kao i liječenje bolesti poput depresije i šizofrenije. Da bi se proizveli organoidi, potrebna je svakodnevna posvećenost u laboratoriji.
We store them at approximately 37 degrees Celsius in our incubators and take them out every day, not just to change the media, but also to look at them under the microscope, to check on them, the progress of the growth, and not just for some days, but over the span of many days, 100 days or even more for some cultures. So it's a long progress that we overlook under the microscope, and yeah, we check the different stages of the growth and can also stain them with different colors.
Eksperimenti u kojima se zrače organoidi ljudskog mozga također bi mogli da otvore put ka terapiji tumora koji su za sada neizlječivi. Zanimljivo je da se u ovoj laboratoriji, pored organoida mozga, uzgajaju i organoidi tumora pomoću alata za genetičku manipulaciju. To nisu prave ćelije tumora, ali su po ponašanju veoma slične njima.
Kada govorimo o tumorima mozga, najčešće govorimo o glioblastomu koji je najzloćudniji tumor mozga za koji ne postoji učinkovito liječenje. Prognoza za ove pacijente je jako loša i oni u prosjeku žive 15 mjeseci nakon dijagnoze. Iako je rijedak slučaj kod djece, ukoliko se dogodi, ova vrsta tumora predstavlja ogroman problem jer djeca uglavnom ili ne reagiraju ili teško podnose standardne vrste terapije.
Iako se sada čini da uspješno liječenje opasnog glioblastoma predstavlja daleki nedostižan cilj, istorija nauke potvrđuje da nemoguće ne postoji. Iskusili su to i prvi pacijenti terapije teškim jonima. U radijacionu salu u kojoj su se liječili sada ulaze naučnici koji je i dalje koriste za razna istraživanja. U ovu prostoriju, u kojoj se 1997. prvi put u Evropi obavio medicinski tretman u jednoj naučno-istraživačkoj ustanovi, danas dolaze i brojni posjetioci koji svakodnevno obilaze ovaj naučni centar sa posebnom radoznalošću za priču o ljekovitim putanjama teških jona. Iako djeluje kao neka muzejska niša sa zanimljivom istorijskom potkom, ova sala je još uvijek pozornica živih, aktuelnih naučnih istraživanja. Tako je ovaj prostor jedinstven u centru GSI po stapanju prošlosti i budućnosti, jer sva ispitivanja koja se odvijaju u njoj po svojoj su suštini futuristička i proći će dosta vremena do njihove primjene u kliničkoj praksi.
I think on the daily basis when you are just doing the small steps in the lab, you do not really feel like you are contributing to something big because it's just your daily routine, but as soon as you see that some method of treatment that was discussed on the conference is undergoing the clinical trial right now, of course it makes you feel kind of proud that you are also involved in this.
We are working in topics that are relatively far from the clinical application. We are way before what is the next one to be implemented. We look for new strategies, new treatment that they might be applied in a long time, like this carbon ion, radioactive carbon ion in this flash. But sometimes some of our studies or part of our studies gets transferred to the clinic, maybe in some special cases or in some. And when this happens, even if it's not maybe my personal study, but it's someone in my group, this become well, it's really rewarding. It's worth a lot because it's. I am a physicist. I will never imagine that something that I do will improve so much. Even the life of one person it's enough to give you the motivation for night shifts and hard work, and it's really something important for me.